Before we talk about DC and AC currents, let's first understand what current even means. Suppose we connect a battery to a bulb using wires. The battery creates a potential difference between its two terminals. The negative terminal has an excess of electrons, while the positive terminal has a shortage. When the circuit is complete, these electrons start moving through the wire from the negative terminal, pass through the bulb, making it glow, and return to the positive terminal. This continuous movement of electrons through the wire is called electric current. The greater the number of electrons flowing per second, the stronger the current. This flow continues as long as the battery can maintain the potential difference. Once the battery's energy is used up, the flow slows down and eventually stops. Now, direct current, or DC, is electrical current that flows in only one direction. Think of it exactly like a smooth, calm river flowing constantly downhill. The water, or the electric charges, always moves forward and never reverses or changes its path. The amount of flow, or the current, might speed up or slow down a little bit, but the direction remains fixed. In a DC circuit, electrons move steadily from the negative side to the positive side of the power source, such as a battery. So conventionally, we make the direction of the current in the opposite direction of the flow of electrons, which means from positive terminal to negative terminal. A battery is the most common source of direct current. Devices like torches, wall clocks, toys, and TV remotes all work on this type of current. Another everyday DC example is mobile phones and laptops. See, if you plot current on y-axis and time on x-axis, the graph mostly appears as a straight horizontal line because the current doesn't change with time. Note that sometimes the current in DC can slowly decrease with time. For example, when a battery starts losing energy as it gets discharged, the important thing is that the direction of flow never changes. The electrons always move from the negative terminal to the positive terminal, no matter how weak the current becomes. So, the graph can sometimes start as a straight horizontal line when the battery is full and might slowly slope downward as the battery drains, but it will never flip below the axis or change direction. Now, let's come to alternating current, which is the type of electricity that powers our homes, schools, and industries. In AC, the flow of electric charge keeps changing direction continuously. That means electrons move one way for a short time, then reverse direction and flow the other way, and this keeps repeating. This alternating happens very quickly. Now you might have seen these graphs of sine and cosine waves. We call a wave a sinusoidal wave, which can either be a sine wave or a cosine wave. In electricity, this shape perfectly represents how AC voltage or AC current varies with time. See, this is one complete wave or one cycle. Now it keeps repeating itself again and again in a regular pattern, which means the wave has a certain frequency, which means in 1 second how many such cycles are repeated. This means that if this is 1 second, then the frequency of this wave is 3 cycles per second, and if this is 1 second, then the frequency of this wave is 2 cycles per second. The shape of an AC current is usually sinusoidal, meaning the polarity of the voltage keeps reversing periodically. This means that the end of the wire which is positive at one instant becomes negative after a short time, and then positive again, and so on, continuously switching back and forth. So this part of the sinusoidal wave, which is positive, implies the terminal becomes positive, and this part of the sinusoidal wave, which is negative, implies the terminal becomes negative. So in one cycle, the polarity is changed 2 times, right? Now, in the United States, we have 60 Hz supply, which means the frequency is 60 or 60 cycles every second, so each terminal changes its polarity 120 times per second. As mentioned earlier, Current always goes from the positive terminal to the negative terminal. But since the polarity itself is changing, therefore, due to this changing polarity, the direction of current in the circuit also keeps reversing. That's why if you connect an AC supply to a lamp, the electrons in the wire move back and forth rapidly instead of flowing steadily in one direction. However, because this happens extremely fast, the bulb glows continuously and our eyes cannot notice the flickering. Mathematically, we write AC current as I equals I0 times sine of 2 times pi times F times T. I0 is this peak current, then F is the frequency, and T is time. This periodic change in polarity is what gives AC its name, alternating current. This sinusoidal nature also ensures smooth power delivery without sudden jumps or sharp changes. Actually, AC is ideal for long-distance transmission because its voltage can be easily increased or decreased using transformers. High voltage means less current, which means lower heat loss. This makes AC more efficient over large distances. Also, most large appliances like motors and fans run directly on AC. In short, AC is the backbone of our power systems because it is flexible, efficient, and practical for large-scale use, while DC is stable and safe for low-power electronic circuits. Please don't forget to like and share this video, and subscribe to our channel.